Hi everybody, this is KBJ-ECE-KSRCT handling linear integrated circuits for you. The topic for today is integrator using op-amp. We have all seen how an operational amplifier works, and now we are going to see how the op-amp is used as an integrator. So, this configuration of the operational amplifier is known to us as the inverting amplifier. How does this work as an inverting amplifier? Is the input is connected to the inverting terminal of the operational amplifier. Here we have the feedback resistor between the output terminal as well as the input terminal, and if we are able to replace this feedback resistor between the output and the input by the capacitor, then the same circuit almost works as an integrator. The supply voltage here is V in and the current is I in. The current flows through the resistor R in. So, this is the circuit. You can see the difference between the previous circuit and this circuit. This is an inverting amplifier. The resistor RF in the feedback loop is replaced by the capacitor C here. The input voltage is V in and the input current is I in, and this current flows through the resistor R in. X is the virtual node, ground node actually. Why do we call it virtual? Is because it is not directly connected to the ground, but even then it acts as a ground because of the property of the operational amplifier, which states that the difference between the current between the input terminals is always 0. So, the non-inverting terminal being connected to the ground, the inverting terminal node X is also connected to ground virtually. That is how we consider it. The current IF is the feedback current which flows through the capacitor C, and it is connected in the feedback. And we know the expression for the voltage across the capacitor as Q by C, where Q is the charge across the capacitor and C is the capacitance of the capacitor. Now, the voltage across the capacitor is given by the difference in potential between these 2 points. So, this point is connected to the output voltage and therefore, it is V out, and this point is actually connected to the node X and we call it as Vx. So, the voltage across the capacitor is given by Vc is equal to Vx minus V out, because the current flows from X towards V out. And as we have discussed already, Vx is virtually it is equal to 0, and therefore, the voltage across the capacitor is given by minus V out. And now, if we take the differential of this, now what do we get? It is voltage across the capacitor is equal to minus V out. We replace this here. So, it is minus dV out by dt is equal to 1 by C into dq by dt, and this dq by dt is the current as Vx is 0. So, now the input current can be written as I in is equal to V in minus 0 by R in. That is how we take this. And the voltage across the capacitor, as we have already discussed, is given by the formula Vc is equal to Q by C, and differentiating with respect to time through the capacitor, it is dVc by dt is equal to 1 by C into dq by dt, and Ic is equal to C into dVc by dt, the same formula which we have discussed already. So, now in this integrator, as we have seen, the current I is given by V in by R, which is shown here, V in by R, and that is equal to Cf into dVc by dt, which is shown here. It is Cf into d into Vc by dt. That is what is shown here actually. So, that is equal to Cf into d by dt of what is your Vc? Vc is given by minus V out, Vc is equal to minus V out, okay, and therefore, you get it as minus V out. Cf is equal to d by dt of 0 minus V out, and therefore, it is minus Cf into d by dt of V out. So, what is dV out by dt? That is minus 1 by RCF into V in of t. Now, I integrate it, I get V out. So, V out is equal to minus 1 by RCF integral V in of t dt, and this is how the circuit acts as an integrator. The output voltage is an integral of the input voltage V in of t dt. The input and output waveforms are shown here. So, here this is a constant step input voltage which is given an input of 1 volts. Now, when you feed this into an integrator, you get a negative ramp. Remember, the input is given in the inverting terminal, and that is why you get the ramp in the negative direction. Supposing I give a sine wave as the input, then in that case I get a square wave output, and when I give a cosine wave, it is a triangular wave. I am sorry, when you give a sine wave input, you get a cosine wave, and when you give a square wave input, the output is triangular wave in the integrator. The limitations of the integrator include the gain actually depends on the frequency of the integrator. So, when f is 0, the gain becomes infinity, and when the frequency increases, then the Xc, the input impedance reduces and the gain increases. Why is this happening? When f is equal to 0, that is your Xc, the capacitive reactance, is given by the formula 1 by 2 pi Fc. So, when f becomes equal to 0, then the input impedance or the capacitive reactance becomes infinite. So, when this capacitive reactance becomes infinite, then the gain which is given by minus Rf by Rn, that is the resistance of the capacitor or the reactance of the capacitor you call it, that becomes infinity, and therefore, the gain becomes infinity. And this Xc actually, when frequency increases, what happens to Xc? When frequency increases, Xc reduces. So, the gain actually depends on the integrator frequency. The frequency response of an ideal integrator is shown here. So, because of this problem that this particular capacitor is dependent on frequency and the gain changes with frequency. Now, it is necessary that we introduce another component, and that component, you see the difference here, you have a resistor in parallel with the capacitor in this feedback loop. So, what does this mean? Now, this is a component, the capacitor is a component which actually varies with frequency, and at low frequencies this becomes, the capacitive reactance becomes very high, and at very high frequencies the capacitive reactance becomes low. But when you have a resistor in shunt across this capacitor, the change in this capacitive reactance does not matter and the resistance remains constant, which means it does not affect the gain of the circuit. Not only is the gain which is affected, because the gain, as you see here, the formula is given by minus Rf by R1. When the capacitor alone sits here, the gain is definitely affected, and when you have a resistor in parallel, the gain is not affected because of the shunt resistor here. Not only the gain which is affected, it is also the frequency response of the practical integrator. You see here, the output gets saturated after a particular point. It remains constant and it gets saturated, and that is another issue for introducing the resistor Rf. So, the gain of the op amp and the response here, you can see the yellow color line, it is nothing but the response of the low pass filter. I do not know how many of you remember, low pass filter has a cutoff frequency FL, and until this particular frequency you get a constant output, and after which the output actually changes. So, the output reduces. So, this is actually same as the low pass filter. Now, you see the 3 dB FL cutoff frequency, and beyond this FL the gain reduces, right. So, FL is equal to 1 by 2 pi RFCF at one particular condition. F naught is the 0 dB frequency, which is given by 1 by 2 pi RFC. So, under these conditions, it is necessary that if this circuit has to work as an integrator, you have to choose the linear region of operation and not the saturated portion, in which case the integrator has to work in this area which is greater than FL, right. But at the same time, it has to be seen that the frequency does not exceed F naught, right. Only if the integrator is operated in this particular portion, this will act as a perfect integrator. Now, what if the signal frequency has to be greater than FL, but how much greater than FL? The condition is given here. The signal frequency must be 10 times greater, 10 times greater than FL. Fs is greater than 10 FL. But remember, once again I tell you, it cannot be greater than F naught. If it goes beyond F naught, then integration will not take place. Okay. So, this is how actually the circuit of a practical integrator works. Now, we take an example to find the lower frequency limit of integration for the circuit shown here. Now, RF is given, CF is given, and R is also given. Now, what happens? Find out FL. FL is equal to 1 by 2 pi RF CF. I substitute RF and CF. Now, FL is equal to 159 Hertz. So, what is our condition which says the signal frequency has to be greater than 10 times FL? Only then the circuit will work as an integrator. Okay. So, now my signal frequency is given as Vm in is equal to sin 2 pi 5000 t. Now, I have to find out what is my Fs. If I find out my Fs, I can tell whether the circuit works as an integrator. What is Fs? 5 kilohertz. Is 5 kilohertz greater than 10 times FL? Yes, because 10 times FL is 1.59 kilohertz, whereas your signal frequency is 5 kilohertz. Definitely the circuit is going to work as an integrator, that is minus 1 by RCF integral V in of t dt.